From a simple apple plummeting to the ground to the majestic dance of planets around the sun, a single force governs these seemingly disparate phenomena: gravitation. It's a fundamental force of nature, weaving its influence throughout the cosmos, shaping the universe as we know it. But what exactly is gravitation? How does it work? And why is it so crucial to our understanding of the universe? Gravitation is the invisible force that pulls objects towards each other. It's what keeps our feet firmly planted on Earth, preventing us from floating off into space. It's the reason why objects fall to the ground when dropped, why raindrops descend from the clouds, and why the moon orbits our planet. Gravitation is a force of attraction. It pulls objects together, regardless of their size, shape, or composition. The strength of this attraction depends on two key factors: the mass of the objects and the distance between them. The more massive an object, the stronger its gravitational pull. Similarly, the closer two objects are, the stronger the gravitational force between them. Consider the Earth and a small ball. The Earth, being massive, exerts a strong gravitational pull on the ball, causing it to fall towards the ground. The ball also exerts a gravitational pull on the Earth, but because the ball is much less massive, its pull is negligible. The story of gravitation is often linked to a falling apple and a brilliant mind, Sir Isaac Newton. Legend has it that while sitting in his garden, Newton observed an apple falling from a tree. This seemingly mundane event sparked a profound thought. If the apple falls to the Earth, could the same force that pulls the apple also be responsible for the moon's orbit around our planet? Newton realized that the moon, just like the apple, is constantly falling towards the Earth. However, instead of falling directly onto our planet, the moon's sideways motion, its velocity, keeps it in a perpetual state of freefall, tracing an orbit around the Earth. This simple yet profound realization led Newton to formulate his law of universal gravitation. This law states that every object in the universe attracts every other object with a force that is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Newton's law elegantly explains why the moon orbits the Earth. The Earth's gravitational pull acts as an invisible tether, keeping the moon in its orbit. The same principle applies to the planets orbiting the sun, stars clustered in galaxies, and galaxies themselves, all bound by the invisible force of gravity. Section 5. Decoding the formula: a closer look. In this section, we will delve deeper into the intricacies of Newton's law of universal gravitation, breaking down each component to understand how they work together to describe the forces that govern our universe. Newton's law of universal gravitation can be represented mathematically with a deceptively simple formula: F equals G times the product of m1 and m2, divided by r squared. This formula, though it appears straightforward, is a cornerstone of classical physics and has profound implications in our understanding of the cosmos. While it might seem intimidating at first glance, this formula elegantly encapsulates the key principles of gravitation. It allows us to predict the gravitational force between any two objects, whether they are as small as apples or as massive as planets. In this formula, F represents the force of gravity, which is the attractive force that pulls objects toward one another. This force is what causes an apple to fall from a tree and what keeps the planets in orbit around the sun. G is the gravitational constant, a fundamental constant of nature that quantifies the strength of the gravitational force. It is a fixed value that ensures the formula works consistently across different scenarios. M1 and M2 are the masses of the two objects involved. The greater the masses, the stronger the gravitational pull between them. This is why larger objects, like planets, exert a more significant gravitational force than smaller ones. And r is the distance between their centers. The farther apart the objects are, the weaker the gravitational force. This inverse relationship is crucial in understanding how gravity operates over vast distances in space. The formula tells us that the force of gravity is directly proportional to the product of the masses. This means that if you double the mass of one object, the gravitational force between the two objects also doubles, and inversely proportional to the square of the distance between them. This means that if the distance between the objects is doubled, the gravitational force is reduced to a quarter of its original value. Understanding this relationship helps us comprehend the delicate balance that keeps celestial bodies in their orbits. Newton's law of universal gravitation is not just a theoretical concept. It has practical applications in various fields, from predicting planetary motions to understanding the behavior of galaxies. It is a fundamental principle that continues to shape our exploration and understanding of the universe. Section 6. Gravitation in action, from tides to space travel. Newton's law of universal gravitation is not just a theoretical concept confined to textbooks. It is a fundamental force that governs the motion of celestial bodies and the behavior of objects on Earth. It has profound implications for our understanding of the universe and numerous practical applications in our daily lives. From the way planets orbit the sun to the way galaxies are held together, gravity is the invisible hand that shapes the cosmos. From the ebb and flow of tides to the precision of GPS satellites, gravity's influence is all around us. It affects everything from the smallest particles to the largest structures in the universe. The tides we observe are a direct result of the gravitational pull of the moon and the sun on Earth's oceans. This gravitational interaction causes the water in the oceans to bulge out in the direction of the moon. The moon's gravity pulls the water on the side of the Earth facing the moon more strongly, creating a bulge. This bulge is what we experience as high tide. A corresponding bulge occurs on the opposite side of the Earth. This is due to the inertia of the water, which causes it to form a second bulge on the side of the Earth opposite the moon. These bulges, combined with the Earth's rotation, create the high and low tides we experience. As the Earth rotates, different areas of the planet pass through these bulges, resulting in the regular rise and fall of sea levels. But gravity's influence extends far beyond our planet. It is a crucial factor in space travel. The gravitational pull of the Earth must be overcome to launch spacecraft into orbit. Once in space, gravity continues to play a role. Satellites and the International Space Station remain in orbit due to the delicate balance between their velocity and the gravitational pull of the Earth. Similarly, the planets in our solar system orbit the Sun due to the gravitational force exerted by the Sun. This force keeps the planets in their elliptical orbits, ensuring the stability of our solar system. Gravity also plays a role in some of the most extreme phenomena in the universe, such as black holes and gravitational waves. These cosmic events provide valuable insights into the nature of gravity and the fabric of spacetime. Scientists continue to study gravity to unlock its mysteries and understand its implications for the universe. Advanced telescopes and space missions are helping us explore the far reaches of space and the fundamental forces that govern it. From the tides on our beaches to the exploration of distant galaxies, gravity is a force that connects us all. It is a reminder of the intricate and interconnected nature of the universe. Section 7. Beyond Newton, the limits and legacy of a law. While Newton's law of universal gravitation revolutionized our understanding of the universe, it wasn't the final word on gravity. Newton's insights laid the groundwork for centuries of scientific exploration and discovery. His law explained how objects attract each other with a force proportional to their masses, and inversely proportional to the square of the distance between them. This was a monumental leap in our comprehension of celestial mechanics and terrestrial phenomena alike. In the early 20th century, Albert Einstein, with his theory of general relativity, provided a more complete and nuanced picture of gravitation, particularly in extreme gravitational fields. Einstein's theory was revolutionary, offering explanations for phenomena that Newton's law couldn't account for, such as the precession of Mercury's orbit and the bending of light around massive objects. Einstein's theory describes gravity not as a force but as a curvature of spacetime caused by the presence of mass and energy. This concept was groundbreaking, suggesting that massive objects like stars and planets warp the fabric of spacetime around them, creating what we perceive as gravitational attraction. The more massive the object, the greater the curvature, and thus, the stronger the gravitational pull. This curvature influences the motion of objects, causing them to follow curved paths, which we perceive as the force of gravity. For instance, planets orbiting the Sun are actually following the curved spacetime created by the Sun's immense mass. This elegant explanation extends to other phenomena such as black holes, where the curvature becomes so extreme that not even light can escape. Despite its limitations, Newton's law remains a remarkable achievement, providing accurate predictions for a vast range of gravitational phenomena. It continues to be used in many practical applications, from engineering to space exploration. Newton's work laid the foundation upon which Einstein built, and together, their contributions have profoundly shaped our understanding of the universe. The legacy of these scientific giants endures, reminding us that the pursuit of knowledge is an ever-evolving journey. Section 8. Fun facts about gravity. Gravitation, despite its seemingly complex nature, can be surprisingly fun. Did you know that you'd weigh less on the moon than on Earth? That's because the moon has less mass than Earth, resulting in weaker gravity. And here's another fun fact. Black holes, those enigmatic cosmic entities, exert such immense gravitational pull that nothing, not even light, can escape their grasp. These fun facts highlight the captivating nature of gravitation. Section 9. A universe of questions. Gravitation, despite centuries of study, still holds many mysteries. What is the true nature of gravity? How does it relate to the other fundamental forces of nature? And what role does it play in the grand scheme of the universe's evolution? These questions continue to intrigue and inspire physicists and astronomers, driving the quest to uncover the deepest secrets of the cosmos. As we delve deeper into the universe's mysteries, one thing remains certain. Gravitation, the invisible force that shapes the universe, will continue to captivate our imagination for generations to come.